So my name is Ganapathy Krishnamurthy. I'm an engineering director for Blob Storage Services at Facebook here in Seattle. And welcome to the first ever at-scale event here. OK, so quick show of hands. How many of you know about at-scale? OK, a small number of people. I'm hoping that there are someone who is not a Facebook engineer in that group. All right, so I mean, building high-scale and highly reliable services brings some unprecedented challenges, right? So how do you scale your service from millions of users to billions of users? Or how do you actually store and process vast amount of information so that you can get the insights to either drive new experiences or like drive efficiencies? Or how do you actually build tools so that your engineers can scale to operate these increasingly complex systems with high reliability while staying agile, okay? So I wish there were textbooks or papers on this, but there isn't, okay? So at-scale started a few years ago as a place where engineers can sort of come together, connect and share their experiences and insights, the things that they're actually been on topics that are similar, right? Example, spam fighting. And an open and collaborative community leads to cross-pollination of ideas and better systems and better services for users. I've been part of the Seattle tech community for many, many years. And I've seen the tech ecosystem in Seattle really grow. We have startups like Datto, who you would be hearing from later, driving deep innovations in technologies like machine learning. We have distributed campuses of pretty much every big tech name, like Google, Facebook, Twitter, EMC. And we have the Amazon and the Microsoft here, and many, many other tech success stories. So a few weeks ago, I reached out to this community to set up the data at scale. And the response that I got has been amazing. So we have an excellent lineup of speakers from 8 different companies today, and we have you, the audience, representing about 60 different tech companies in this area. So this is an amazing and exciting day for the Seattle tech community. Thank you for actually making this possible. All right, so we have an awesome agenda of talks today. The day is actually split in 3 sessions with a break for lunch and coffee in the middle. And each session is focused on a very specific technical area. So first session is actually focused on data processing at scale. So we have talks on queries. We have talks on search at scale. We have talks on machine learning at scale. And we have talks on visualization at scale. The second session focuses on distributed like data storage or structured storage. And the third session focuses on having how to manage data at scale, but on a budget. Okay? So, and we have at the end of the day a happy hour where you can actually mix and mingle with other engineers who attended the event. So thank you for spending the day with us. I'm confident that you would find the talks insightful and the stories engaging. And make sure that you make some new friends. After all, it's paid for by Facebook. So you have to friend somebody. So let's get started. Please welcome Eric from Facebook, who's going to talk to us about Presto on Sharded MySQL.
My name is Eric Huang, as G2 mentioned. I am an engineer on the Presto team at Facebook. Just real quick, how many of you guys have heard of Presto? Great. I was making a bet earlier with Martine as to how many. That looks like I lost. So, well, let's get started. So today I'll be talking to you about how we can use Presto to power user-facing analytics with sharded MySQL as the backend. This is a relatively new deployment of Presto at Facebook. And so I'll go a little bit into the background of Presto, why we chose sharded MySQL as the backend, the features we felt were necessary to build this, and finally, the abilities we can derive from this architecture. So a little bit on Presto. Presto is an open source distributed SQL query engine. It is also designed to be NC SQL compliant, which makes it compatible with a lot of services out there. The goal of Presto, as we were building it, was to design a system that would allow data scientists or users even just to do quick interactive data analytics over their data sets. We started this project in 2012, specifically targeting the use case of our Hive data warehouse scientists, those data scientists for a Hive warehouse. At the time, they were kind of, as they were developing their hypotheses and they're exploring their data sets, they're kind of struggling along to use Hive to try to do these types of analyses. Because Hive, as some of you may know, is designed to do batch analytics, right? So it's good for doing ETL pipelines. It's good for running these long jobs that take many, many hours. But if you're a person sitting in front of a UI, you're a person sitting from that terminal typing those queries, it's really not the best of all experiences. So the ability to do quick, interactive data analytics is a very powerful tool for exploring your data set and for discovering those new and interesting data trends. And so that's what we really want to focus on with Presto. After we open sourced Presto, we've seen the community grow by quite a lot. So we have a number of companies out there now who have adopted Presto as their warehouse analytics solution. And we've seen others out there starting to offer Presto as even a cloud service. And just last week at the Hadoop Summit, if you guys were there or listening in, we've had Teradata just announce that they're also going to be joining the community and that they're going to be providing enterprise-level support for Presto. So Presto is designed around the idea that we should get results back to the users as quickly as possible. Let's take a look at the architecture. So initially, we have a client. It sends a SQL query to our coordinator service. The coordinator parses and analyzes this text, and then produces a distributed execution plan. Then it takes this distributed execution plan and passes it to the scheduler module, which is also part of the coordinator. Now, this scheduler module will inspect this plan and figure out what logical tables we need to scan, and then talk to a data location API. This data location API will tell us how to break those logical tables into these small processable chunks. Then we can take these chunks and the plans, and then we ship it out to all of the workers. So typically, a SQL query will include at least 2 different stages. And that's because usually at the bottom, you have to read the data from something. So that is at least the first stage. And at the top, we have an output stage that collects all of the results together and buffers it for the client. Intermediate stages here can include things like aggregation operations and join operations and so on. And so the other responsibility of the scheduler then is to take all of these different stages and wire them all up together so that the workers know how to talk to each other. Now, within a stage, a single operator, we've designed them to be as streaming as possible. So this means that we can pipeline the execution, which allows us to get results, when possible, back to the clients, even before we're done perhaps even scanning the whole table. And that way, if you're a user sitting in front of your terminal, you can see the results starting to come back, and you can start working at it and looking at it, and maybe even cancel the result, or cancel the query if you've seen enough. Another key design feature that we have with Presto is that the execution only moves as fast as the client can consume that data. So the way this works is we start off by running the query. The initial results get buffered up into this buffer, and then we wait for the client to pull that buffer. The execution doesn't proceed until some of that data has been pulled out or emptied. And this way, we keep up with how fast the client is pulling, and if the client is slow or blocking, we don't have to waste resources on it. So the whole design of Presto is to minimize latency from data to user. So with that, we've taken a fully in-memory model of execution, and we've taken a fast-fail model of execution, which means we don't think it's necessary to retry in the event of failures. We think it's possible just for the client or the user just to resend the query, especially if it's fast, if they see some transient errors in the process. Now, as we were designing this system, one thing became apparent to us. As we're initially targeting the Hive storage engine, but it turned out that we could actually extract out this storage interface into an extensible storage interface that we could bind in other things into. And so that's exactly what we did. It turns out that Presto has just 3 different APIs that you need to implement in order to become a Presto connector. And that is First, you need a metadata API, which describes all of your data in terms of logical tables and columns and their types. You need a data location API that tells you how to take a logical table and break it up into these small processable chunks that we can then schedule out. And finally, you need to have a data stream API, which says, how do we take these chunks that you've told us about earlier and turn them into streams of records that we can execute on? And so that's the part that has to sit in the execution engine. So all you have to do is implement these three interfaces, and it turns out that any data source that has a tabular format or can be represented in a tabular format is compatible with this. So as a result of that, we've seen a lot of contributions, both internally at Facebook and externally from the community, in providing new connectors. So some of the connectors that we currently have now are Hive, and we have many HDFS variants behind Hive. There's Cassandra, there's Kafka. We support anything that is JDBC compliant. We can pull that as a data source. And we've even modeled the JVM as a connector by providing the JMX counters as a 2-column table, which is pretty cool, because then you can run a query over your entire service and just see how your servers are doing, or the VM is doing. We've also had teams at Facebook, such as our newsfeed team, who've implemented connectors that allow them to introspect and debug on their systems. So the newsfeed team has this connector that lets them query their index servers so that they can debug it when things and issues start arising. A common theme here that you might notice is that all of the connectors that we have are that they are over existing storage systems. Now, we said Presto is an analytics system. And many of these connectors are the storage engines. They're not actually analytic storage engines. And those that are designed to be analytic storage engines are not actually tuned precisely the way that makes Presto really move quickly. So then that poses the question. What does a connector that we can customize and tune for Presto's specific model of execution look like? And the answer here is, it depends. It depends on a lot of things, right? It depends on the query rate that you expect. It depends on the query complexity that you expect. It depends on how reliable you expect your queries to be, and ultimately, it depends on how deep your pockets are here, because you could spend a lot of money on the system. So really, there's not one solution out there, and so the best you can really do is maybe just target and hone in on a specific use case that works really well for you, and then maybe provide some knobs along the way so that you can tune to fit exactly what you need. So in the last few years, we've seen an increasing demand for user-facing analytics platforms. Sometimes we call these insight platforms. Let me give you an example. Parse. Parse is our mobile app development framework. External developers who build their apps can use it to build and run their apps, and we also collect some information for them. So that means they naturally want to be able to ask some questions about how their app is doing. For example, how many users do we have today versus last week? How do our users break down by different demographics that may be tagged with each user? And finally, as a software developer, I want to know how bad my last build has been crashing, or actually the build before that even. So just like our data scientists, we want to empower these external developers, well, external users in general, to gain insight into their data sets through very fast interactive analytics. And so this is the use case that we've decided to tackle with Presto. Now, this leads to a few requirements that we have to consider. The first of all is that this is user-facing. So, well, user-facing system, it's got to be fast, right? And it's got to be not just fast, but consistently fast. Having really inconsistent performance for users is one of the most annoying things you can have. Second of all, it's got to have really, really high reliability because it's got to be up 24/7. When you do upgrades and you do deployments, you can't bring the system down. And it's got to be really scalable because we expect both the query volume and the data volume to grow organically over time. And much of this we expect, as we talked to a number of customers on this front, and that data growth and the query volume growth is often super linear. So you got to be ready for that. And finally, you got to have update semantics. And you'll ask, why updates? So a lot of these systems, it turns out that they actually want to submit queries over pre-aggregated data. And that's good, because you want to do as much of your work ahead of the time as possible, right? So that you can run your queries faster. So that means you usually have to have a system that is actually producing pre-aggregated data for you, right? So in a lot of these cases, you have a system that's doing these live updates or live roll-ups of some kind of streaming data set, right? And it's usually rolling it up over, say, an hour or some kind of time frame, right? So unless you want your data to only become available for queries by the end of that time frame or that hour, then you really want to allow that roll-up system to be able to flush its counters, the partial values down every, say, like 5 to 10 minutes so that it becomes available for queries. And that's why you need updates. So what storage engine did we end up choosing for Presto? I say that rhetorically because it's in the title. Yes, we chose MySQL. Now, the first question you ask is why? So MySQL at Facebook has come a long ways. It's one of our most stable and most battle-hardened systems out there. It literally powers the core of the website that you see today. And we've done a whole lot of work in performance tuning this system. For example, we've tuned it to work really well on top of Flash. And it turns out in our earliest performance benchmarks while building the system that MySQL running on top of Flash had one of the most highly performant and consistent profiles that we've seen out of the systems that we tested. It comes out of the box fully DR ready with its replication. And itself is a full database engine, which means, well, we don't have to worry about how we're going to map a Presto tabular schema into this system because it already has a tabular schema. And then it lets you get around tough questions like, how do you want to represent nulls in your data set? It also naturally has update semantics, so we get that pretty much for free. Already built up around it, we have a lot of existing tooling and automation that we can leverage. And so these are all things and experience and know-how that we can leverage to move us forward at much faster paces and not have to worry about building and reinventing the wheel again here. So when I'm talking about MySQL, obviously I'm not talking about a single instance of MySQL. I'm talking about many instances of MySQL spread out over many machines. You can almost think of this as forming a smart bucket store, if you will. You can group some of these servers together, and then let's say we determine some static number of shards for this group, and then we can assign them out to these different servers. So let's say we assign shards 1 through 4 to server 1, and shards 5 through 8 to server 2, and so on. In this case, we can map a single shard to be a MySQL database. So this gives us very natural semantics then, and very natural tooling, then to just move shards/databases around. The other thing that we do with the shards is that we give them all the same schema. So then if you look at a single shard, it looks like every other shard except for the data inside of them. Shard migration is also how we can scale out the cluster. So typically, we have many more shards than servers. And as the data set grows, or if you get hotspots, you just migrate them off onto new servers, and then you're good to go. So now let's say we have a table. Let's call it my table. And we want to distribute that data across these shards somehow. How do you run a query? Well, the easiest thing you can do, let's say you're given this query, select star from my table where x equals 5. The easiest thing to do here is just to blast a MySQL query out to all the shards and then collect up all the results. Easy, done. You can also see here that it would be really easy to do predicate pushdown or early shard evaluation of the predicate to take the work off the hands of Presto just by rewriting those MySQL queries that we're blasting out and push them into the shards. Having a lot of shards compared to the number of servers in this case also gives us plenty of I/O and CPU parallelism. So that gives us our performance in this case. So now what if we know a little bit more about how we've distributed the data? Let's say we know that the data is hash partitioned on the column x. Well, in this case, then you know that x equals 5 can only live in a single shard. So that's the only shard we need to send the query to. And then you're done. There's no point in talking to anything else. So now we know how to talk to all the shards for a Presto query, and we know how to talk to a single shard for a Presto query. So what if these two options themselves are not good enough? For example, talking to all the shards gives you the parallelism that you need, but because you're talking to more machines and more servers now, that exposes you to an increased risk of failure. It also increases the risk for stragglers because more machines means you might have more risk for variability in your query runtime. On the other hand, you can mitigate this by talking to a single shard, but obviously that limits your concurrency and creates a potential hotspot in your data set. So what do we do? What you can do here is go with a bucketed sharding scheme. So this works well if you can assume or if you can predict that your query will typically have a predicate such as x equals some constant in it. If you know that's going to be there, then you can choose a sharding scheme that can leverage this fact. So you can choose a sharding scheme that for a particular value of x, you can control that it only sits in 1/n of your total shard set. So in this example, where x is put into 3 buckets, that means for a particular value of x, it can only be found in 1/3 of the total shards. Note that I also have to mention another arbitrary column y here, because we need another column in this case to give us the entropy we need to determine the exact shard for which we want to place a row. And this is because we want to make sure that the placement is deterministic, and that allows us to find that shard again if we ever need to update it. So now let's say we take that bucketed sharding scheme, and we take the same query that we had from before. To run that exact same query, we can now send it to exactly 1/3 of the total shards. And so now this gives us sort of a tuning knob that we can play with to control how much fan-out and parallelism that we want. So more buckets gives you less parallelism and less fan-out, and less buckets gives you more parallelism and more fan-out. So they're kind of inversely related like that, and you can tune them back and forth. What we've actually implemented in the Presto on Sharded MySQL connector is a recursively nested version of this. But the concept, the high-level concept is pretty much there. Now we've talked a little bit about how we're placing data into shards and sort of the strategies around that. Let's talk a little bit about what goes into the actual shard themselves. So we said we were using MySQL. And MySQL, we use the InnoDB storage engine, which stores each table on disk as a B tree. So what this means is that with the InnoDB storage engine, the B tree that is chosen is lined according to the primary key. So that means if you can play with that primary key, you can basically control how the data is laid out on disk. You can think of this as clustering or maybe changing the sort order of your data. Any access along these different dimensions will be very efficient both for point lookups and range scans. And since you're playing with that primary key, if that changes your uniqueness semantics, you're going to want to add a new unique secondary index to enforce that uniqueness constraint, and then you can get around that problem. So let's look at an example. Let's say you have a table, the same table as before, my table, and it's clustered on x and y. So I've represented it in this case for each shard by giving it a table that's sorted on x and y, and those are functionally equivalent. Now to run a query that says something like select star from my table where x equals 5 and y greater than 2, then we will rewrite this as MySQL queries from the Presto query and then pass them down to the shards. And each instance of MySQL will then be able to walk its own B tree and figure out exactly just the pages it needs to answer this query. So in systems like these, it is very important for minimizing I/O access to retain consistent and fast performance in production. And I would say every production query that we have has to be optimized like this in some way. Otherwise, you end up scanning all of your data for a query, and that's bad because the data set will grow over time. Now, another interesting property that you get from clustering is that you basically get another free sort order out of it. So how does this help us? Let's say we have an analyst, and that analyst wants to ask the question, how many users have taken a specific action at least 10 times? So they might write a query that looks something like that. And given no further information to Presto, Presto would generate the following query plan. And so this query plan says, first we'll start by scanning the data out of my table. And then we'll have a first level aggregation that computes the count per user. And then we'll filter on that count per user. And then we'll produce a final count across the users and then output that data. Now the gotcha here is in the first level aggregation. The problem is you need to buffer every single user in that entire table until you've seen the last row, because you don't know when the count is complete until you've seen the last row. It makes sense, right? And this is fundamentally very dangerous because, especially in a production system, now you have a query that runs with memory requirements linear on something on the input. So that's something we would not allow in a production query. How do we get around that? Now let's say we do the following. Let's say we first shard the data on user ID, which means a single shard will contain a unique set of users. And then we cluster on user ID, which means that shard can then produce those users in sorted order. If we do that, and we put into the Connect the ability to report this to Presto, Presto can take advantage of that fact and produce a more optimal plan. And so this is the plan that it would generate. You'll see the main difference here is that the first level aggregation is now fully streaming. And the reason we can do that is because as you see your first user, you can start counting. And as you see the user IDs change, you know that all of the previous users now done and seen complete. So you can now flush that out. So it basically turns your requirement for memory from linear on the input to basically constant. And so that's extremely powerful. Clustering your data gives you a free sort order. And it's important for memory-constrained queries, making them feasible in a production environment. So at this point, we've talked about how we're going to place data into shards and the different ways we can tweak the data on disk to make that faster. What happens if you want to optimize for potentially different query patterns? Because all of those things allow you to optimize for just a single set of query patterns. We allow schema designers to actually define multiple layouts for a single logical table. A layout is a physical representation of a logical table, and a logical table can have one or more layouts. You can, in the backend, we actually map a layout to a physical MySQL table, and you can think of that as almost a full copy of the entire data set, potentially with different attributes. So different layouts might be clustered differently, and they may be sharded differently, have different compression attributes, and so on. The other thing you might realize is now that if we have different layouts, we potentially have to write a single row into different places, which means you have a multiple write problem and potentially a consistency problem. So the way we've dealt with that is we've gone with an eventually consistent data model so that at any point in time, the layouts might be inconsistent with each other, but they will eventually and quickly converge to the same values. And it turns out that this is usually OK with the customers of the system, so long as they don't see their counts rolling backwards, because that's when they really start freaking out. We mentioned earlier that we've tuned MySQL to work well with Flash. And in general, that gives you the best and most consistent performance, especially under high concurrency. But the downside is that it gets very costly if your data set gets very large. So we're looking at some cheaper alternatives, and we're building out new machine classes that have large spinning disks, and it's very data dense, but also has a Flash cache on top of that, so that we can optimize if your data set has hot, cold data semantics. And we've seen that this is generally the case, and it works because a lot of big data tends to have some kind of time element in it, in the cases that we've looked at. And for the most part, most people like to look at what is more recent than what is older. And so that's why this generally plays out. Now, we've talked about a number of different dimensions on which we can tune the system. For example, we've talked about how we can control parallelism and fan out. We've looked at adding more layouts to optimize for query patterns versus the storage cost of having those layouts, using an all-flash machine solution versus a data-dense disk plus flash cache solution. And there's also the streaming execution versus efficient filtering discussion. I actually didn't really talk about that one, but if you look through some examples, it turns out they're sometimes at odds with each other, so you have to make that trade-off. But the most important feature here is that we're actually providing these as tuning options to each product team, so that they can tailor for their specific needs and their budget. So we talked a little bit about Parse. But we also have a number of other Facebook systems that are supported by this Presto and sharded MySQL solution. And this includes products in the ad and the mobile space. In aggregate, the system currently hosts something like several hundred terabytes of data. And this number is expected to grow significantly by the end of the year, as we have a number of new customers that are in the pipeline to be onboarded. And the data itself is naturally growing as well. So that'll also add to that load. So what's next? If you've been following Presto in our code base, which is in GitHub and is available to everyone, you'll notice that we're also working on a new connector called Raptor. So Raptor is our native column store designed explicitly for Presto, and it's tuned to provide just the semantics that we need to get performance for analytic queries. So in general, you guys might know that columnar storage solutions are better for analytic queries than our row stores like MySQL. So this is something that we hope to move forward to in the long term, but because we're building this from the ground up, it's still very much an alpha, and it lacks the stability and maturity and all of the ecosystem that we've built up around MySQL. So more on that later. So the summary of this is, Presto has an extensible storage interface, and we've leveraged that to target the specific use case of user-facing analytics. And to do that, we've designed a solution around sharded MySQL for storage. The customizability of the system is key, and it enables product teams and insight teams to tune for their specific query workloads and make the necessary trade-offs when possible. The other thing that this opens us up to is Presto is traditionally thought as existing in the warehouse analytics space. And so this is our first step into pushing Presto into a user-facing system and into a product-facing system. Thank you. That is all. Any questions? Yes?
Well, yeah, the question is on the sharding. Do you replicate the shards?
Yes. So the question is, can you replicate the shards? And the answer is yes. MySQL does this out of the box by having a master-slave model, or master with n number of slaves. What we actually have in MySQL is something called semi-sync. So every time you write to the master, it forces that write to go to n number of slaves before it's considered committed. And that's how we make sure we don't lose data.